We're talking about electromagnetic induction. So here are the Maxwell's equations. Okay. What the equation will be referring to in this, or the chapter is based on this equation. So what does this equation tell you? This is called the Maxwell's Faraday equation. On the right hand side is what do you have? Cause. And this is the effect. Okay, what this equation is telling you is time varying magnetic fields produce electric fields. What can you do with electric fields?
Particles.
Right. So you put a wire, you can drive a current in it. Okay. Also, magnetic fields can exert forces on moving charges, and they can deflect them. Okay. So these are the two equations on which this equation and this part of the equation is what the chapter is based on. Okay. Let me give you an example of this. Okay. So time varying magnetic fields will produce electric fields. So here's a situation. Okay, so this is just a solenoid, a coil of wires, and it's connected to an ammeter. What does an ammeter do?
Measures current.
Yeah, measures currents. Okay. So here's a magnet that's producing a magnetic field. Now if you hold the magnet at rest, okay, this is what we want to see. This is the equation we want to see. You hold the magnet at rest, magnetic field is not changing with time, there won't be any electric field produced. Nothing happens. Now if you move the magnet in this location, the magnetic field is changing. This term is non-zero. Okay? And what you find is when you move this, so when you move this in this direction, when you move the thing downwards, the electric field is, it'll induce an electric field in this direction, like that. Okay. So if you're moving the magnet like that, it'll induce an electric field everywhere. Okay. And the further out you are, the weaker the field is. That's the configuration of the field. And now you stick a wire, voila, there's a current in the wire. No batteries. Okay. So as long as the magnetic field is changing, okay, you're generating an electric field, and the field can drive currents. So sounds like you got free electrical energy. Yeah, there you go. So the work you did, okay, got converted to electrical energy. Yeah. So here's you saw that. What is this fellow? Very good. So this is the same thing as that. What is happening here? Okay, so here's a coil. There's the coil not connected to battery, and they're not connected. And what we're going to do is when you close the switch, then there's a current flowing in this, and it was not a magnet, and then it became a magnet. So for that fraction of a second, the magnetic field changed, and for that time where the magnetic field was changing, you'll have a current induced in this. So anytime you close and open the switch, you're changing the magnetic field, and you'll induce an electric field. Okay. All right, so here's the deal. If you have a magnetic, and I want you to remember this the rest of your lives. Okay, so here's the magnetic field, and if you increase this magnetic field, all right, let's do a different color. If you increase this magnetic field in that direction, you will induce an electric field like that. That'll be the configuration of the electric field. Okay. And what do? Stick a wire there and you get a current. Yeah. You don't have a wire there, and well, you don't get a current. All right. So anytime, now you know, anytime you have a situation where you're changing magnetic fields, you can turn that into an electric current. Okay? So that's very important. And we use this in many, many applications. Okay, that's how a microphone works. Well, what do you do on a microphone? So here's a microphone. You talk into this microphone. What happens? The diaphragm gets pushed back and forth. Well, you want to convert this into an electrical signal.
So you touch magnets.
Very good, my friend. So I've given you all pieces of information. You attach a magnet to the diaphragm. The magnet moves back and forth. How do you convert it into an electrical signal? Stick a wire there. There you go.
What's the efficiency on that, like moving a magnet to cause an electric current?
Oh, well, with these phenomena,
I feel like it can't be that much energy.
no, yeah, it's 100% efficient. The only all right, so here's a yeah, it's 100% efficient. I don't know how to give you a clean answer, but so where you can ask this question is in a dam, in a windmill, how much of the kinetic energy is converted to electricity? Okay. And any energy lost is because of friction in the bearings and stuff. But anyway, I haven't thought about it and I don't have a clean answer, so, but my knee-jerk reaction is 100% efficient. All right, so what are we learning in this chapter? Anytime the magnetic field changes, you can change that to an electric current. And you saw how a speaker works. And now I'll show you how an electric guitar works. Okay, so okay. So for an acoustic guitar, you pluck the strings, and just the vibrating string doesn't make enough sound for you to hear it. So you need some kind of an amplifier, okay, or a resonator. Well, amplifier. So this air box is the resonator. It amplifies the sound. Well, an electric guitar doesn't have that. So how do you amplify the sound there?
Analyze magnetic difference when
What's that?
strings vibrate.
What's that?
Analyze magnetic change in the strings.
So yeah, that's what you do. Anything vibrating, all you do is stick a magnet to it. So here's the string that vibrates, magnetize that. Here's the pickup coil. That vibration is changing the magnetic field. That's converted to an electrical signal here. And you send that to an amplifier. Okay?
The guitar strings are magnetized?
Yeah, that area is magnetized here. Yep. So now you know how to convert any motion into an electrical signal. Okay. Just take a magnet and put a pickup coil nearby, and you're all set to go. All right, so that's what we're going to learn today. Okay? All right, so what do we want to remember? Anytime you're changing the magnetic field, you're inducing an electric field, okay? And so, yeah. So stationary and moving charges produce electric fields. Charges produce electric fields. Magnetic fields are produced by moving charges as well as changing electric fields. Okay, so here's the Maxwell's equation corresponding to that is this. Okay, what the statement is saying is magnetic fields are produced by moving charges, that's the current density, as well as by changing time-varying electric fields. Okay, we'll talk about this in one of the next chapters. Okay, in this chapter, what we are concerned with is this equation. Okay. Time-varying magnetic fields producing electric fields. Okay. Now it turns out that the nature of this electric field is different. I showed you that if the magnetic field is increasing, the electric field is produced like that. This is the electric field. And the line integral of this electric field around a closed loop is not zero. The electric field produced by this electric field, the line integral of this electric field around a closed loop is zero. Okay? So this is called a conservative electric field. This is called a non-conservative electric field. Okay, that's just the electric field nature is different. That's all. Okay? But it's nothing we have to worry about. Okay? So, okay, I don't want to confuse you guys, but in this chapter we're looking at time-varying magnetic fields producing electric fields. Okay, and here's a picture to remember. If the magnetic field is pointing this way and it's increasing in magnitude, the electric field produced is in that direction. Okay. And again, what do you do with the electric field? If you choose, you can stick a wire there and it'll drive a current in that wire. Yeah. All right. So now we'll define magnetic flux. Yeah. Flux is denoted by phi, the subscript B telling you it's magnetic flux, and it's defined as B dot A. Okay, so here's a magnetic field in this region, and the magnetic flux you can think of as how many magnetic field lines are going through this area, okay, penetrate this area. So right now, how many field lines penetrate this area? 0, okay? And if the area is at an angle, there are fewer field lines penetrating this area than this guy. Okay, so we define the magnetic flux as just like we've done previously for the electric flux, B dot A. Okay, where A is the area vector and B is the magnetic field vector. Okay, so Mr. Faraday came up with this law. And what he said was the EMF around a closed loop, okay, the EMF induced around a closed loop, this integral that I talked to you about, this integral around a closed loop is the EMF. Okay, that's what Mr. Faraday was talking about. That's the voltage induced around the closed loop. That's what's driving the current, okay? So the EMF induced around the loop is negative of the rate of change of the magnetic flux through the loop. Okay? So what he's saying is, here is the loop. The EMF induced around this loop is equal to negative of the rate of change of flux through that loop. So if the magnetic field, the flux through that loop is changing, the EMF induced will be equal to that. This is Faraday's law. Okay? The negative sign is related to this fact. Okay, when I said the magnetic field is increasing in this direction, the electric field is in that direction. Okay? If you have a current in this direction, so let's understand the negative sign. Okay. If you have a current in this direction, the electric field will drive a current in this direction. What is that current, loop of current acting like? What is a loop of current?
Electromagnet?
It's very good. It's an electromagnet. Okay. So what is this beast acting like? It's acting like a magnet. Which way is it producing a field?
Coming out of the center.
Yeah, in the upward direction. Look at this. What is producing it? An increasing magnetic field is producing it. What is induced is trying to oppose what is producing it. Okay. And that's Lenz's law. Okay. The induced EMF or the induced current is such that it opposes the change that's producing it. Okay, and that's what that negative sign is about. Okay. So we'll talk about it later. Okay, so anyway, here's Faraday's law. The induced EMF in this loop is equal to negative of the rate of change of flux through that loop. All right, now the flux you saw was B dot A, it's equal to BA cosine theta, dt, time rate of change of that. All right, so now, if you want to induce this EMF, now it turns out that you can generalize this. We started off talking about changing magnetic fields. Now you could do the following, okay? So as long as this is non-zero, you have an induced EMF. So let's say we don't want to change B, but we can change the area. Okay, and the flux changes. How do you change the area? You can go back and forth like that. Okay. Go back and forth like that. You'll have an induced EMF in this loop. Okay. You could change the angle. Okay, so here is this area. You could rotate this guy. Okay, so you're changing the angle. Theta can be a function of time. Okay, and you're inducing an EMF. And it turns out that in practice, that's the easiest thing to do. Rather than changing B, moving the magnet back and forth, or changing the area, changing the angle is the easiest. Okay, so let me show you that. There. So, in this diagram, there's the magnetic field. Okay. We keep the magnetic field constant. Okay. The magnet constant. Here's the loop of wire. The area of the loop of wire is constant. What we'll do is we'll rotate the loop. We'll change the angle. Okay. So the EMF induced will be minus d by dt of BA cosine theta. And you have an EMF induced. How do you change the angle theta?
Spin it.
Spin it? How do you spin it?
Using electricity for the magnet?
No. In a dam, the flowing water turns it. In a windmill, the wind turns it. In a thermal power plant, I'm sorry?
Steam turbine.
In a nuclear power plant,
Steam turbine.
steam. In a natural gas power plant,
Steam
steam. In a diesel generator, you burn diesel. The goal is to turn that thing. All right? Okay. So there's Faraday's law. Okay. So again, like I said, it turns out you can vary anything with time, B, A, or cosine theta, or a combination of those three. But in practice, theta is what you change with respect to time. Okay. And you have an induced EMF. Okay. So here, now that you understood it, okay. So what is it that we're going to remember? Anytime you have changing magnetic fields, you can induce a current, and once you have electric current, you can do a zillion things with currents. Very easy to handle that. Okay, so if this guy moves, the bulb will light up because the magnetic flux through this thing is changing. As long as this thing is moving, the bulb will light up. As soon as this guy stops, the bulb will not light up. You move this guy, the flux through this guy is changing. So it's relative motion that matters. Here, the area is changing and the bulb will light up. This is the only case where the bulb won't light up. Okay. Right. How about this guy? So this current produces a magnetic field like that. As long as this guy is moving parallel to the wire, the number of field lines through that is not changing. So you won't have any current through there. When this guy moves away in this direction or that direction, the flux through this thing is, and what is happening? Huh? Yeah, it's decreasing. Okay, so, and it's decreasing the fastest here, and the induced current will be the largest here.
What do you mean when you say decreasing in that context?
Okay, the field is stronger here, and as you go there, the field is getting weaker, so the flux is. All right, so Lenz's law talks about this negative sign, okay? It tells you the direction in which the EMF is induced or the current is induced, okay? So here's what happens. So if you move the magnet in this direction, you're increasing the flux through this loop, and the induced current will produce a flux in the opposite direction, trying to opposing the change that produces it. Okay? So when the magnet moves in that direction, the flux through this thing is increasing, and the induced current is producing a flux in the opposite direction. When you move the magnet in this direction, the flux through this thing is decreasing, and the induced current produces a flux in that direction, opposing that change. Okay? And that's what that thing is related to. So polarity of the induced EMF is such that it opposes the change in flux that produces it. Yeah. All right, now we'll talk about the second part of this. So this guy. Magnetic fields exerting forces on moving charges. All right, so let's see what happens. Okay. So in this diagram, you see a magnetic field into the plane of the paper. And what we'll do is we'll take a metal rod. Okay. What is a metal rod? I mean, what does a metal rod have that a piece of wood doesn't have? Yep. Free charge particles, okay? So now what we're going to do is move this metal rod in that direction. Well, you're moving the charges as well along with it. Okay? So if there was a positive charge, the force on the positive charge when it moves in this direction is V cross B. The force on this positive charge will be in that direction, and the force on the negative charge will be in the opposite direction. So as long as you're moving the rod, these forces will make the charges collect here and the positive charges collect there. How long will they collect there? Well, once enough positive charges collect there, they oppose the force on this positive charge, on the positive charge. When the force is balanced, the charges have stopped collecting. But this has become a battery. There's a potential difference that develops. So all you have to do is, in this room, there's a magnetic field in this direction. Okay? That's north. You take a rod and move it. This end becomes positive, this end becomes negative. You can connect this to a light bulb and light a bulb. It turns out that if you're moving perpendicular to the magnetic field. If you move parallel to the magnetic field, there's no force on the charges. It won't be a battery. The voltage developed is the magnetic field strength times the length of the rod times the velocity. This is for a perpendicular velocity. All right, again, free lunch. Okay, so what is going on? What is it that you're spending?
You're spending energy to move.
Yes, so the work done, the rate at which you're doing work in moving it is what's being converted to electrical energy. Okay, so it turns out that, well, why do you have to apply a force? You get it moving, and if there was no friction, it would keep moving on its own. It turns out that once a current starts flowing, the force due to the magnetic field is in the opposite direction. So you have to keep applying that force. Yep. All right, so here's the applied force. You have to apply that force because when current starts flowing through this thing, there's a magnetic force on the thing in the opposite direction. Okay? And that's why you have to apply force. Okay? So when a moving conductor is in the magnetic field is part of a circuit, the induced voltage is equal to the rate of change of flux through the loop. Okay, so when you move this thing, the flux through this loop is increasing, okay? And the induced EMF is equal to the rate of change of flux. The flux is equal to the magnetic field times the area. X is this distance and L is that distance. And you take the time derivative of that, only X is changing. Okay, so it's BLV. Because of the induced current, a magnetic force arises in the conductor, and the magnetic force is in this direction. Okay? And so you have to apply a force to keep it moving. Yep. And so all you're doing is using this device, you're converting the work you do into electrical energy. So here's the rate at which you're doing work, applied force times the velocity, and that is equal to the electrical power produced. So the rate at which you're doing work is equal to the electrical power produced. Yep. Again, there's never a free lunch. So work done by the applied force is converted to electrical energy. Okay. So you can use Lenz's law to figure out the direction of this current. Okay. So for instance, when you move this to the right, the flux through this is increasing in the downward direction into the sheet. So the induced current should produce a flux opposing that change. Okay. So if you stick your hands out like that, see the induced current is producing a magnetic field outside the paper. Okay, so this induced current is producing a magnetic field like that, which is opposing the increase into the sheet. All right, so what did we say? You have a magnetic field, all you do is take a rod, metal rod, and move it. I guess you can't move parallel to the magnetic field. If you move it perpendicular to the magnetic field, that's when you get the maximum voltage. You get a voltage. So they tested this out using big toys. Okay, so there's a shuttle, and here's a 20-kilometer long rod. This is the Earth's magnetic field. Okay. So a satellite was tethered to the shuttle by a 20-kilometer cable. The wire was oriented perpendicular to the Earth's magnetic field. They should have seen a potential difference of 8,000 volts. Okay, and a voltage of 3,500 volts was measured. Probably charges leaking out and stuff. All right, so I said this electric field is non-conservative. What does non-conservative mean? Conservative means the work done is path independent. Non-conservative means the work done is path dependent. Okay, but anyway, so here's another definition of non-conservative. The line integral around a closed loop is not equal to 0. Okay. And so if you increase the magnetic field in this direction into the sheet, what you'll have is an induced electric field like this, and the line integral of this electric field is non-zero. Okay. So this electric field, the nature of this electric field is different than the nature of the electric field produced by these charges. Okay. For this electric field, the line integral is 0. Yeah. Okay, so in our lives, the most convenient form of energy is electrical energy. Okay? And so here's how we set it up. So you just saw that, okay, you induce a voltage as long as you can change, as long as the magnetic flux changes. And like I said, the technologically most convenient thing to do is change theta as a function of time. Okay. So here's a setup. So if you have a wire like that, and if the wires are connected to the rings, and the rings, there's brushing against the ring, and the voltage that this load sees with this connection is an AC voltage like this. If you connect that wire using a split ring, the voltage you see is that. Okay. So this is a DC generator. Now there are ways of smoothing out this waveform, and we'll talk about that a couple of chapters later. Okay? And so, for instance, your computer doesn't like this voltage. Your computer likes this voltage. Okay? 9 volts or something like that. Okay? And so we'll learn how to convert this and this waveform to a DC volts. Okay. And do you have your brick? Okay. Anybody have your brick? Do you have your brick?
What?
Do you have your brick?
Oh, sure, yeah.
Okay, so that guy converts this thing into that. That's what that guy does.
It's very hot while doing it.
Yeah. It's not very efficient. All right, so again, so we saw how to turn this loop, okay? So there's trillions of dollars invested in that thing. Okay, so what this is saying is the amplitude of this, so it's a sine wave that you're generating. Omega is the angular velocity of the loop, okay? And the amplitude of this voltage is N, is the number of loops, number of turns in the loop. A is the area of the loop, B is the magnetic field strength, and omega is the angular frequency. Okay. So the voltage that you're getting out of the wall is 60 hertz. That is, you have 60 cycles per second. Okay. And it turns out that, okay, the bulb, the brightness of the bulb goes like this, 120 times a second. So bulb is going on and off 120 times a second. How come you don't see the flickering?
It's too fast for our eyes to see.
Yeah, so anything faster than 30 times a second, you can't. So if the wire is connected to the outside brushes like that, that's the signal you get, that's the voltage you get, yeah? All right, so I don't know if you guys have seen a toy like this, but again, what is the deal? What happens if you change a magnetic field? Yeah, so it produces an electric field, okay, which can drive a current. Okay, so here's a coil connected to a battery. When the switch is open, there's no current flowing in this, it doesn't produce a magnetic field. When you close the switch, a current starts flowing, and so it produces a magnetic field. So the magnetic field has gone from 0 to non-zero value for a very short time. And so in the time the magnetic field change, here's a ring of wire, flux through that thing changes, and it produces an opposing field. So if this guy produced a magnetic field like that, in the ring, the induced current will produce a ring magnetic field. And they'll repel each other, and this ring will jump. And go to John Marco again, he'll show you a ring that'll jump from the ground floor to the ceiling on that thing. Mm-hmm. So you can, have you guys ever seen those rings jump? No. Do you guys know what this is? Huh? Yeah, what does it do?
It prevents the circuit from blowing up the fuse and blows there instead.
Okay, so here's what it really does. Okay, you all have it in your houses. Okay. All right, so let's say you're using a hair dryer. For a minute, I didn't know what that was called. Anyway, all right. So you have current coming through here like that. And let's say this wire breaks, and the wire breaks and hits the housing. You're holding on to it. And so now the current will go through you instead of through to the wall. And you don't want that. Okay, so how do you stop it? Or you can take this thing. Yeah, you could do this experiment. But maybe not. Okay, anyway, plug it in. So it's live. Throw it in the bathtub. Okay. All right, so let's see what will happen. Okay. All right, so here's the incoming current. The incoming current, again, this is the rule. You stick your thumb out in the direction of the current, and your fingers, right hand,
Yeah.
produces the magnetic field. So this guy will produce a magnetic field in this direction. The current going out like this will produce a magnetic field like that. So what is the net magnetic field through this thing? If the currents are equal, the magnetic field through this thing is 0. Now you take that and throw that in the bathtub. Now some current is leaking out through the water, and the currents are not equal anymore. So the magnetic flux through that was 0 when there was no leakage in currents. The instant there's a leakage in current, this magnetic flux is non-zero. Soon as the magnetic field through this thing changed, what happened?
The electric change.
It induced an electric field. There was a current in this thing, in this coil. You can use that current to switch it off. That's what that does. And it'll switch off the current in a millisecond. Okay, so it's a safety device. And, yep.
Is that the thing like you push to reset?
That's
the
right.
outlet?
Yep. You have it in your garage and in your bathrooms. Yep. So, in my house, outside, whenever it rains and the water gets in the outlets outside, the covers are not well sealed. It had to go in the garage and reset it every day. All right. So you saw that how to turn motion, vibration into an electrical signal. Yeah, so that's what happens in all electric instruments, musical instruments. Yeah. So, have you guys heard of electromagnetic braking?
Yeah.
Mm-hmm. Yeah. So that's a very safe way to brake. And do you guys know what is the cheapest mode of transportation?
Boat,
Hmm?
along water.
Yeah, on the boat. Next cheapest, train, and then the truck. Truck is the most expensive way of transporting stuff. So why do we transport everything by truck? It's the fastest way and convenient. All right, so we could transport more stuff by train if you guys have seen train tracks. Do you see trains moving all the time? No. Yeah. So if we could, if trains could do what Amazon can do, next day delivery, shoot, you wouldn't see a truck on the road. And, one of the things you would like is more trains, okay, on the tracks. Now, if you could guarantee that they won't collide with each other and stuff like that, it would be safe if you could do that. Okay. And electromagnetic braking could do that for you. All right. So, here's a metal. If this swings between a magnet, okay, so as this thing is swinging, see the magnetic flux through this thing will change, because as it's coming there, the magnetic flux through that metal is increasing, and that will induce a current in the opposite direction, okay? So when it's going like that, this will induce a north pole there, and this north pole will repel that north pole, so it's slowing it down. Okay? When it goes away, when it's going away, this will become a south pole, this will attract that, and it'll slow it down. So it's adding friction. So if this magnet was not there, this would swing forever. If there's air friction is negligible. With the magnet present, this will stop very fast. Yeah. So these are called eddy currents. Okay. You can do the same thing on a train. Okay, so all you have to have is a loop of wire like that, and that loop of wire is hanging close to the track. Okay, when you want to stop the train, all you do is you flip a switch, pass a current through this loop. Now this has become an electromagnet, a strong magnet. And as the train is moving, this becomes a north pole, the eddy current, this is a south pole. This is pushing the train back, this is pulling the train back. Yep. And you'll have a nice, smooth, fast stop. You won't even spill your hot coffee. Okay. Here's how metal detectors work. Okay. So let's say this metal, without this metal detector, without this metal, you're passing an AC current that is changing the flux through there, and in the receiver coil, you're inducing a current. Okay, so if there's nothing passing, you're inducing a high current there. Soon as a piece of metal passes, this is inducing a magnetic field in the opposite direction. The magnetic flux through here decreases. The current amplitude decreases in the receiving coil. Okay. And that's how metal detectors work.